day. So we're back again with another lesson for statics of rigid bodies. So I'm your lecturer, and this is my contact details. So our topic for lecture 2 would be about force vectors. So last time we are introduced to fundamental concepts, the basic quantities, and the unit systems, as well as we are given some guidelines and tips on how to approach the problem solving uh, in statics. So now we will be introduced to force vectors. So for now, we will start with definitions of scalars and vectors, and in particular the force vector. So there are other vectors that we can that are involved here in statics, but now our focus would be force. So for this chapter, we'll be learning about the adding of forces, or and resolving a force into components using parallelogram law and triangle law, and to also express force and position in Cartesian vector form, and explain how to determine vectors magnitude and direction, and also an introduction to dot product, to find the angle between two vectors or the projection of one vector onto another. So we will be starting with two-dimensional, and eventually we'll be exploring three dimensions. So let's first define what is scalar and what is vector. So it is written here: a scalar is positive or negative physical quantity that can be completely specified by its magnitude. Examples are length, mass, and time. So we have discussed before, introducing our basic quantities, that out of the four, only force is a vector, and the first three, length, mass, and time, are all scalars. They are completely specified by their magnitude, and they don't have they don't need you don't need to specify a direction for them. Whereas a vector is also a physical quantity, but it requires to have a magnitude and a direction for its complete description. So our concern now is the force vector, but you can also have what you call the position vector and the moment. So more on that later when we will be exploring about that product. So defining a position vector is also essential in uh, in 3D. Okay, so this is what will be the graphical representation of a vector. We have an arrow with a tail, and an arrowhead, its head, denoting its direction, and denoting its line of action, and an angle denoting its direction, and the length of the arrow will be the magnitude of our vector. So if you see something like this, an arrow with an angle and a line of action, that would be our vector. In this particular case, we'll be dealing with force vectors. So some vector operations. So vector operations is not really as simple as algebraic multiplication, division, but there are similarities, but keep in mind that we are going to operate on vectors mostly acting on different lines of actions and different directions. Okay, so first rule for multiplication and division: if a vector is multiplied by a positive scalar, its magnitude is increased by that amount. Okay, so if you multiply a vector a by 2, that would be 2a. If you multiply it by a negative scalar, the directional sense will change. Okay, so if we multiply the vector a with negative 1, the arrow will reverse, but it will still be the same line of action, but the arrowhead will reverse. Okay, so that's for multiplication and division of a vector by a scalar quantity. So now we go to a very important technique or method that will come in handy for all the operations or the calculations that we will be doing as we progress through the topics here in statics. So we have vector addition by parallelogram law. So as you can see, the basic idea would be to form a parallelogram and analyze the lengths and the angles inside and between the vectors. So if we have two vectors a and b, okay, so please keep in mind that when we write vectors, we are writing it in boldface. Okay, if you see anything in boldface in our calculation, that is representative of a vector. So a scalar would be in not in boldface. Okay, so here we have vectors a and b, both are in boldface. So this is vector a going into this direction, and b this direction. So what we want to do is to add this vectors. So by the parallelogram law, what we need to do is to put the two vectors tail together, as is shown in the figure here in B. So vector A, this is the tail, and vector B is the tail. So that is the two vectors now form an edge of the parallelogram. So what we need to do is to draw parallel lines to both the vectors. So this line is parallel to vector B, and this line is parallel to vector A. And the point of their intersection now closes the parallelogram. So now we go here in letter C, we trace a diagonal here in the inside of the parallelogram, this blue arrow here. So from the tails of the two vectors that we join together up to the intersection of the parallel lines to them, and this intersection at point P here would be the head of the what we call the resultant vector. So when we add vector A and vector B, that will be equal to a resultant vector. Let's name it R. So the operation is R would be equal to vector A plus vector B. So that is now our parallelogram law. Another way to do vector addition is by triangle law. So the earlier technique is composed of constructing a parallelogram, but this time, you guess it right, this is by constructing a triangle. So the same thing in A, we have here two vectors that we wish to add, vector A and vector B. So the method is different here. From the parallelogram law, that is tail to tail. Now this is head to tail. Okay, so we have vector A This is the tail of vector A, and this is the head of vector A. The head of vector A would be connected to the tail of vector B, as you can see here. So that would be vector A plus vector B. Now, the last thing to do is to draw a line from the tail of A to the head of B. So it's somehow very similar to the parallelogram law, but this is just one side of that, or half of that. You can see here the blue arrow, which is the resultant, is still, if you complete the earlier parallelogram, it's the same measurement, the same magnitude, and the same direction. So for the triangle rule, that would be R is equal to vector A plus vector B. That is drawn in this way. Or we can also write it as vector B plus vector A, where the tail of A is connected to the head of B. And again, from the tail of B, we trace a line up to the head of A, and that would be our resultant vector. So I hope you are getting the concept of so as you know, we are dealing with parallelograms, triangles, so they have sides and they have internal angles. So okay, so let's go to vector subtraction. So vector subtraction is very similar to addition, in a way that you will also use the parallelogram law, and you can also use the triangle law. So we have two vectors here, vector A minus vector B. In this case, this is vector B, but since this is subtraction, this will have a negative sign, so the head will be reversed. As we have learned earlier, we multiply it by a scalar, a negative 1, it will be reversed. So the same thing for parallelogram law, you trace a parallel line for both the vectors and get the diagonal, and the direction of that diagonal would be the direction of your, let's name this R prime. Okay, so this is R prime is equal to A minus B. Both are vectors. So the same for the triangle construction. So that would be A minus B. So the head of A with the tail of B in the opposite direction, that's negative B, and we complete the triangle, and that would be the length of the R prime in the direction of the R prime. Okay, so just for you to better visualize it, we have here a hook with a chain attached to it. So if we will draw a free body diagram of that, so the chain is evidently in tension, right? So we can write here, we have a force 1 here, force vector 1, and force vector 2 here. And since if we can make these measurements, we can resolve these forces pulling the chain, or the hook, into a resultant force F sub R. And this is the same as doing the parallelogram law or the triangle law, whichever you please. So we have here another there's a connection here, there's a force 1, maybe a chain, and a force 2 pulling on it, and we can resolve that into a resultant force. We can write this down as the resultant force is equal to force 1 plus force 2. Okay, so I mentioned earlier that since we are dealing with triangles, parallelograms with lengths, with edges, with sides, with angles, internal angles. In order for us to make sense of this, the values here, we need to brush up on our, of course, on our trigonometry and trigonometric functions. So I hope you will review those, since those will be very helpful and very much essential in problem solving here for force vectors. So now let's go to components of a force. So earlier we learned to find the resultant of two vectors by doing vector addition and vector subtraction. So now what we want to do, we are given one force vector and we are asked to resolve it into given axis. So in this case, we have the u axis and the v axis. You can also have the x axis and the y axis, which are perpendicular to each other. But some of the problems here, the two axes where you need to resolve or determine the components of a resultant force or a force vector, would not always be perpendicular to each other. Alright, so we have here a force and we will be asked to resolve it into a v and a u axis. So that would give us f sub v, the component in the v axis, and f sub u, the component in the u axis. So what does this look like? It just looks like you will reverse your parallelogram law, right? So here we'll still draw a parallelogram. So for this one, the axes are specified for us. Here we just need to extend this axis as well as this one, and we find the components of the force in those axes. So we can also write it as a triangle in such a way, like this. But I think it's better to draw the parallelogram first before you do the triangle. So this one, we draw the parallelogram, and what they did is they what do you call this? They transpose this force into the side. Since this is the same direction, this is a different line of action, but this is the same direction and the same magnitude of force. So it doesn't really change the vector. So it's permissible. Okay, so as I mentioned earlier, we need to brush up on our trigonometry, and this is the cosine law and the sine law is a very useful tool for us. So just to refresh us, we have here a triangle. So we have 3 internal angles for the triangle. So the total internal angle of a triangle, we know, would be how much? No, sorry. It would always be 180. So 180 degrees. So here we use small letters for the internal angles, A, B, C. So A plus B plus C should always equal 180 degrees. So now we will denote the sides of the triangle as capital letters. Take note, capital letter of the angle opposite that side. For example, here we have the internal angle A, small letter, and opposite it is capital A, the length of that side, as well as B, internal angle B, and the opposite length would be capital B, and same goes for C. Okay, so the cosine law gives us the length of one side, in this case C, or whatever you wish if you want to look for A or B. But the idea is to find the length of one side given the length of two sides and the angle opposite that unknown length, right? So this one is C is equal to the square root of the sum of the squares of the two other sides. That's A squared plus B squared minus 2 times A times B, the cosine of the angle opposite the unknown. Okay, so I hope at this point you memorize this equation. It will be very useful. And as well as the sine law, where it relates the sines of the angles of the opposite lengths to the other angles and lengths. So A over sine A would just be equal to B over sine B is equal to C over sine C. So this will be we will need to have a review or a good background in trigonometry in order for us to make sense of this parallelograms and this triangles in our discussions. Okay, now let's see what if there are three forces that we need to resolve into a resultant force. So we have like vector 1, force 1 plus force 2 and force 3. Force 1, 2 and 3. So as you can see here, it is better to resolve two forces first. In this case, F1 and F2. So by doing a parallelogram law here, we can resolve that into a force. Let's call it F1 plus F2. There's really no assigned variable here. It's simply this one. This vector is the resultant of F1 plus F2. Then now we have F1 plus F2 vector and F3 vector. So that leaves us with two vectors, and then again we can apply the parallelogram law to get the final or the resultant vector for the three vectors. So later on in the examples, this will be clear these concepts. Let's have a sample problem. So this is sample problem number 1. We'll see how we can apply our recent learning about parallelogram and triangle rules to find the resultant of these two forces. So as you can see, there is a screw eye and it is subjected to two forces. We have F1 that is given as 100 newtons and F2 given at 150 newtons. Take notes of the direction of these two vectors. So F1 is 15 degrees from the horizontal axis or the x-axis, and F2 is 10 degrees from the vertical axis or the y-axis. So our first step is to draw this figure free from the surroundings, or we will draw a free body diagram. So here is our free body diagram. We have F2 at 150 newtons, F1 at 100 newtons. This is 10 degrees from vertical, this is 15 degrees from horizontal, and here we use the parallelogram law by drawing two parallel lines to F2 and F1, and then from the origin we extend diagonal to the point of intersection of the two parallel lines, and that is the resultant of F1. That would be, the resultant would be equal to F1 plus F2. Again, this is vector addition. So now we know what the orientation of the resultant, but what we don't know is its magnitude and its direction, whether measured from the vertical or measured from the horizontal. So now we know that here, this, if you can see this, we have 15 degrees here, but the angle we need to know is this one. So we just add this angle to this 15 degrees and we can determine the direction of the line of action of the resultant force. Okay, so now that's our first step. We should be able to draw the free body diagram correctly. Okay, so we should draw the free body diagram in order to know what givens can we work with and what are the unknowns. Okay, so now let's write down what are the given. This will already be enough if you ask me. This is already the given. So let's just write that down again here. So we have F1, which is 100 newtons, and F2, which is 150 newtons. So what is the required? So again, we need to determine what we can work with and what are we looking for. So in your solutions, please always be complete and write the given first and then what is required, so that will give us an idea if you understand the problem and if you understand what the problem is asking. So required is, let's go back to determine the magnitude and direction of the resultant force. So it means we need the magnitude of FR, it's unknown, and the direction. Therefore, we need to get this angle here. Okay, so that's all what the problem is asking. So now let's go to solution. What is our solution to this problem? Okay, so we learned recently about cosine law. It's just a review. Cosine law and sine law. So now we can picture that this is let me somehow transpose the line. Okay, so I transposed F2 here. Okay, so now we have this triangle. So we can use sine law and cosine law to determine the unknowns. Now let me just write that down again. So F2, this would be F2, 150 newtons. So basically, we have a triangle with two sides known, right? So this is one side, that's 100 newtons. This is another side, that's 150 newtons. And FR is unknown. So by using the cosine law, we can know what this unknown is. But now, what else do we need? We need the value for this angle in order for us to let's call this angle C, a small c. So we're looking for this theta, which is opposite now the force F sub 2, and we also want to know what is C. Okay, now let's work on what we have first. So we know that this is a 90 degrees, right? This axes are perpendicular to each other. And we know that this is 15 degrees and this is 10. So that's a total of 25. So if this is a 90 degree angle, so what would be the measurement for this? So that would be 90 degrees minus 25, which is 65 degrees. Now we know that, I hope you can see my writing, even the stroke is thin. Okay, so we know that this is 65. So what is the total of the internal angles of a parallelogram? Let's go to the parallelogram first. So that would be 90 times 4. So that's 360. So the total internal angle of a parallelogram is 360 degrees. We know that this is 65, and the opposite is also 65. These are properties of internal angles of a parallelogram. So this is also 65. So what we are left with is this angle and this one, which are also equal. So if we subtract the two 65 angles from 360, which is the total internal angles of a parallelogram, we can now get this angle and this one, which are just equal. So the answer, we will just divide by 2. Okay, so 360 minus that 65 and 65, that's 130. So we are left with 230. So we have 230 degrees. That is not yet the angle. We need to divide that by 2. So divided by 2. Now this this small c, okay, c angle would be 230 over 2, or that's 115 degrees. Okay, now that we have a value for this, I will write that down here. This is 115 degrees. So now we can apply the cosine law. So let me write it down. So according to the use the cosine law in order to find the value or the magnitude of the resultant force. So here we will just be applying cosine law with our variables, but please recall that the cosine law says that C is equal to the square root of A squared plus B squared minus 2AB cosine C. So here we write it as F resultant force equals, that's F1 squared plus F2 squared minus 2 times F1 and F2 and the cosine of the angle that we solved earlier, cosine C small, which is this angle, this one. Okay, so plugging in our values, and please ready your calculators for this. This is how you write your solutions. This is what I expect to see on your problem sets. Okay, so 100 newtons, and also never forget about the units. Okay, so you will get point deductions if you don't include the units. So that is what we discussed in lesson 1. So that would be the requirement. So let me just write it down here. 2 times 100 newtons times 150 newtons and the cosine of the angle. Cosine 115. So since this is over 90, I think this would be a negative. This would be a negative value. And since negative times positive and minus, that would be plus. Okay. Oh, sorry. There is a plus sign here. Okay. So as if we let's examine what will happen to our units, because we need dimensional homogeneity. So this is 100 newtons squared. So the unit would be newton squared plus, this is also newton squared, minus newton times newton, that's also newton squared. Okay, so inside the radical symbol we will be having a consistent unit, newton squared, and since this is the square root sign, the final unit for our answer would be just newton. So that's square root of newton squared, that's a newton. Okay, so now let's plug this in our calculators. So that would be cosine 115. Okay, it's a negative value multiplied by 150 newtons multiplied by 100 newtons times 2. So I have an answer. We store it in a variable in our calculator, and we have 100 squared plus 150 squared minus the first value that we stored. So I have the square root of, this is the square root of 4,178.54785.547. At this point, I don't want you to round anything, since we are continuing on our calculations. So since we are using scientific calculators, utilize the save function in your calculator. Okay, so we need to find the square root of this, and that gives us, it gave me 212.555 newtons. Okay, so this would be our answer for the magnitude of the resultant force. So in your calculators, this is still a value 5524591. So I want you to store that value, since we are still going to use it to find the angle. And how are we going to do that? By using law of sines. So now we have a known angle, which is, this is 115, right? Opposite the FR, which is also known, and we want to know this angle, and this angle is opposite F2. Therefore, we can write, if you can recall, we write sine law in terms of our variables. So FR all over the sine of our C here, C, this small c, is should be equal to F2 and our theta. That is just, sine theta. That is just the same as saying A over sine A is equal to B over sine B, or equals C over sine C. So we just wrote it here in terms of our own variables here, which is FR, F2, theta. So plugging in the values, since again, please use the value in your calculator. So for this example, I will just, for just short writing, I will just use up until 0.55. But we need to still use the exact values in our calculator up unto this point. So that's 115. That would be equal to F2, which is 150 newtons all over the sine of theta. So here the unknown is sine theta. So rearranging that equation, let me go here on this side. Okay, rearranging that equation, we have now since we transpose sine theta to the other side, so we have sine theta equals 150 divided by, so we transpose this one on this other side to 212.55 newtons. Again, reminder, use the stored value in your calculator multiplied by the sine of 150. So then we will get the sine of the theta, which we will be just using arc sine so that we can get theta. So let me perform the operations. That 150 divided by 212.55 multiplied by sine 115. So I got 0.6395, and I will get the arc sine of that. So arc sine of, now I got theta equals 39.76, or if we will write that in, that's 39 degrees 45 minutes and 40.19 seconds. Okay, so you should be familiar with the calculator you're using in order to get this value. But the value that resulted is 39.76 degrees. Okay, so now we should be writing our answer. So now we got the value of, or the magnitude of the FR, and we should be able to draw it. Okay, so here, let's draw our answer. So I'm just using this function, so for ease we have that's F2, we have F1, and the resultant, let me draw the resultant. Okay, so this is, you can use the parallelogram law, but this is for just for the sake of displaying the answer. So now our answer would be, just rewriting, oh sorry, okay, so there's a mistake. Let me do that again, sorry for that. So this is your resultant, and let us write it as the FR would be 212.55 newtons. And earlier we know that this is the theta we solved is this value. Okay, this is theta, this is 39.76 degrees. But what we need is the angle, this angle. So how do we get it? We just add it by, we know that this is 15, so that would be this angle, let's call it phi, the direction of, so this angle would be equal to 39.76 plus 15, that would be 54.76 degrees. Okay, so now we already, this is the answer. So I expect you to compile your answers after your problem solving. Okay, so for every problem that you will be given as problem set. Okay, so we can say that our FR, or our resultant force, has a magnitude of 212.55 newtons and is 54.76 degrees from the x-axis or the horizontal axis. So this is x and this is y. So remember that it won't always be x and y axis. You can have u and v axis which are not perpendicular to each other. Okay, so please be very careful about the angles. Okay, so this is our answer now. we have the magnitude and direction of the vector, and you need this drawing, okay, so that we can see the line of action of the vector. Recall that the vector is composed of magnitude, direction, and line of action. Okay, next example, we will be doing the opposite. Now we have a resultant force, and the problem is asking us to resolve it into specified axis. So if you can notice, we have here the u-axis and v-axis, which are evidently not perpendicular to each other. Okay, so our task is to resolve the horizontal 600-pound force into components acting along u and v axis. So our components will be in the u and v axis. So if you can imagine, earlier we are given two vectors and we need to perform vector addition and them to get the resultant. Now we get the resultant and we need to find the two vectors. Okay, so still what I want you to do is follow the format given, required solution, and the final answer. So for now, let's analyze what we have. So we'll just be basing here because drawing in the computer is taking too much time. So the parallelogram here in B, the parallelogram is drawn. So you have you need to draw a line up to the head of, let's say, the first force is F sub u and the other force is F sub v. So here we draw the parallelogram, the same method that we discussed. Okay, parallel line to FV and parallel line to F sub u. So again, we apply what we know of the properties of triangles and parallelograms about their what do you call this, internal angles. Okay, so here in the problem we are given that the u-axis is 30 degrees from our resultant force, which appears to be in the horizontal axis, and here the extension of the v-axis is also 30 degrees from that. So from there we can analyze our angles. So since we know that this one is 30 degrees and these are opposite angles, if you write a line here, if you can recall in your trigonometry, this is, if this is 30, this is also 30. So parallel, if you have two parallel lines and you put another line between them, the angle here and here, opposite angles, I'm not sure if it's really called opposite angles, but they should be equal, this one and this one. So we can write here that this is 30 and this is 30. So in properties of the triangle, the internal angles will always sum up to 180. That's why this is 30 plus 30, that's 60. The total should be 180. So now we know that this angle is 120. Okay, so we will just be dealing with this triangle with 3 known internal angles, 1 known side, and 2 unknown sides. So the best way to proceed here is to use the cosine law. So we are given, so if you will go back to that illustration, that triangle could already be your, should be on your given. So let's write what is given. We have FR is equal to 600. This time our unit is pound force, 600 pounds, and it's let's draw the triangle here. We have, we have this vector and this vector, which are, this is f sub v and this is f sub u, and the internal angles are 30 degrees, this is 120 degrees, and this is 30 degrees. Okay, and this one is, this one is 600 pounds. So what are we looking for? What is required? Required is, I think it's asking for the magnitude and direction. Oh, sorry. We're just looking for magnitudes. Okay, so we're looking for FU and FV. Okay, so for the solution, we will be using the sine law, since it is the easiest way, since we know all the internal angles, we know one side, so we can find sides. So let's name the sides. Let's say the FR, or 600 pounds, is A, FU is B, and FV is C. Now therefore, the internal angles here, opposite C would be small c, opposite B would be a small b. Okay, so B, the small b would be equal to 120 degrees, and small a would be equal to 30 degrees. Okay, so our sine law says that A over sine A sine small a would be equal to B over sine B. We just gonna plug in our variables in this cosine rule. So we'll just be using A and B first. So A is 600 pounds all over the sine of small a, which we say is 30 degrees, and that should equal B, which is f sub u, all over sine of small b, which is the angle B, 120 degrees. So manipulating this equation, we get that f sub u would be equal to the sine of 120 degrees all over the sine 30 degrees and multiplied by 600 pounds. So let's examine the units first. So this is sine 120 degrees would be unitless, sine 30 degrees would also be unitless, and the final answer should get the unit pounds. Okay, so let's plug that in our calculators. So f sub u would be equal to 1039.230485, or we just round it to 0.23 pounds. Okay, so we are just looking for the magnitude, so this will be our final answer for FU. So now let's go finding FV. So we can write FV as in the same way. So 600 pounds, let me rewrite it, 600 pounds all over sine 30, that would just be equal to FV over the sine of its opposite angle, which is also sine 30. Okay, so what does that tell us? So since we have FB opposite 30, looks like we will be getting FV is equal to sine 30 over sine 30. Multiplied by 600. So sine 30 will just be cancelled. So we know that FV would just be equal to also 600 pounds. So that is our answer. I hope you have an idea how to apply the parallelogram and triangle rules or laws in order to resolve force into components, and also to find the resultant force of two force vectors. So all this you can read in Engineering Mechanics Statics, still by Hibbeler, page 17 to 26. You can study the remaining examples there. So thank you for your attention.